Jai Hind all. Myself Dr. Sanjay Sharma. I'm faculty in the Applied Science Department. Today I'm here to basically discuss one very important topic from engineering mathematics, and the topic is concerned from module number 2, which is differential calculus 1. Today we are going to discuss the topic, and the name of the topic is Leibniz theorem. This topic is very highly important topic from this model number 2, and this is very applicable in your engineering. You can say most of the engineering subjects. It cover most of the nth differentiation. I mean, whenever you're supposed to differentiate a function higher times, right? So you must want to use the application of this Leibniz theorem. So in this lecture, I'm going to take the statement, how the Leibniz theorem applicable and where, and how we use it and how we apply this theorem, right? And later I'm going to discuss the examples based on this topic. So let's move in with the Leibniz theorem. So look, suppose we are having two functions. One function is u, another function is v. Both the functions having the x variable. Both the function must be of the dependent on u, on x basically, right? Then it's showing the how we get the application, or we get the basic concept behind this theorem is, if you're going through the first time differentiation of the product of two functions, then it is usually called that. You can say you can keep the v same, and you are going to differentiate the function u. Similarly, you need to take u same and you should differentiate v. Okay. So this is basic fundamental behind the differentiation of the product of two function only. Okay. This is the product rule. Of course, we are aware about that. Now, if we look the nth differentiation of two function, see here I am going to differentiate this function one time. But here we have applied this theorem n times. So the statement is look like this. It is the nth differentiation of the product of u and v. And here, this is the first term of the theorem. In this term, you need to take nc0, where c represents the combination, right? The n time differentiation on u, and you must keep the v same. The fundamental is from the you must keep one function as unchanged, and you must apply the differentiation on the rest function, right? So here we have to apply the function n time. Similarly, now we must take the nc1, and we are going to take the less differentiation on u. So here we have differentiate u n minus 1 time. Now we take the one time differentiation on v. This process is going on right now. So this is going like c nc2, and then differentiation of u n minus 2 time. Where is the differentiation of v is going to 2 times. Whenever it reaches up to a point like ncr, then n minus r time differentiation must be on u, and the r time differentiation must be on v. At the end, we have to reach on the point ncn, and the all differentiation on u are over, and we reach to the n time differentiation. So this is the logic behind the Leibniz theorem. It can cover the product of two functions when the product is going to differentiate to n times, right? So this theorem can also be written in the form like the n time differentiation of u v supposed to be n time differentiation of u, then v same, and student nc1 is always n, so you can take n here. Similarly, nc2 supposed to be n minus 1, n into n minus 1 2, and this is going on. So this is the statement of this Leibniz theorem, correct? So let us take some example where we can apply this Leibniz theorem and how we take the differentiation of some function. Okay, so here I have taken one example. In this example, I need to take the differentiation of the y2. Y2 is get product with 1 minus x square, then x and y1, then m square y. Okay, here m is a constant basically. You are not supposed to differentiate this m, right? So when we open up the Leibniz theorem, so we are going to use the Leibniz theorem here. So it can be written as, see, first of all, the theorem is going to implement on this term, later on this term, and later on this term. So here we can see, student, this is a y2 function. Y2 mean the differentiation of y already taken 2 times, okay? And 1 minus x square is a function of x, where y2 is also a function of x. So now the problem is how we identify that which term is going to u and which term is going to v. This is the main fundamental before applying this theorem. Okay, so let us discuss how to get the u. Okay, so u can be obtained by only one way. You must select u only those functions of x whose nth differentiation, see, nth differentiation is well known to us. Okay, so this is the story behind the selection on u. Okay, now how to get the v? So v can be obtained by only selecting the term whose differentiation is going to decrease and it is going to convert in absolutely into 0. So this is the story where we have to select u and v. So in this question, basically in this part, as you can see, 1 minus x squared, it's a polynomial of degree 2. So by making 2 time differentiation of 1 minus x squared, it's supposed to be a constant. One time it should be 2x, and second time it's 2, and third time it's going to 0. So here we must take 1 minus x squared as v, okay, and this is y2. See, what is y2? When we differentiate one time y, we get y1, okay. When we differentiate again y1 with respect to x, we get y2, okay. So you can see, if we are going to differentiate this y n time, then what will be the result? You can see here, the y2 is going to n time, so it should be yn plus 2 time. So the agenda is basically we get all time of differentiation on y2. There is no problem. If someone going to tell us that you should differentiate y2 100 times, then the total answer is supposed to be 102. So we get the all time differentiation on y2. It should be denoted by u here, okay. And the differentiation on 1 minus x square is going to decrease. 2 times it is definitely 0. So we must take 1 minus x square as v. Now you can use and you can apply the Leibnitz theorem very easily. See how. This is y2 and you're supposed to differentiate this y2 n times. You must keep the v same, that is 1 minus x square. In second term, you need to differentiate this y2 n minus 1 time, and c1 is supposed to be n. Then here you should differentiate this 1 minus x square 1 time with respect to x, so it reached to 2x. In the third term, here this is the value of mc2, which is n minus 1 by factorial 2. Then the n minus 2 time differentiation of y2, and then 2 time differentiation of 1 minus x square, which is minus 2. So here you can say this is the and on the of the Leibniz theorem on this term only, right? Now this d2 power n supposed to be here, then you can see we have taken minus here. Now similarly, as I have explained already there, so it is obvious now that you should take u as y1 and v as x. You can see, check here, the differentiation of x is going to decrease. It should be v, and the nth differentiation or any number of differentiation of y1 is obviously well known to us in advance basically. So here, keeping the same things in mind, you should take the n time differentiation on y1, you should take x, keep x as unchanged. Later on, you should nc1, then n minus term differentiation on y1. You can see the differentiation of x with respect to x is 1. So here, the and of the Leibniz theorem on this term basically. Okay. Now, we have to differentiate m square with y, but you know, as I have already informed you, this y m square is a constant, so there is no need to apply the Leibniz on this m square. So now we take the n time differentiation of y. So student, here is the basically detailed explanation how we basically choose the parameters, the variables, okay, and then how to apply the Leibniz theorem on these variables. So now finally you can keep up the values which we have applied over there. So see, y2 is a 2 time differentiation with respect to x function, and you have differentiated it n times. So the total supposed to be go yn plus 2. You have keep 1 minus x square already, 1 minus x square, that should be unchanged here. Nice. Then this is 2 and this is n minus 1, so the total goes to yn plus 1. 2x is same, minus is there. Then y2 after taking n minus 2 time differentiation supposed to be yn, and student minus 2 is same here. You can keep minus outside. Later on, this is y1, and then by taking n time differentiation on y1, it should be yn plus 1. Then 1 on n minus 1, you can see n minus 1 plus 1, that should be n. So yn is here, and it's supposed to be yn, as you can see carefully from here. So this is basically your dn. Moving forward, so it is your answer basically now by making all the necessary actions. And you can see first term is yn plus 2, then yn plus 1, then yn, then n plus 1. So you can see there are 2 yn plus 1 here. So we need to assemble all the yn plus 1. So student take 2x as common. See yn plus 1 as a common. You can keep 2n plus 1 inside a bracket. Similarly, you can see yn is also on 2 to 3 places. There you can see yn, there are yn, there is also yn. Then you have to merge. So this is basically the answer when we apply the Leibniz theorem on these 2 or 3 terms. Correct? So now, moving forward, I have one more example, very important example for you here. See, what is the question? The question is, when y is equals to x log 1 plus x, then you should prove that the yn, the n time differentiation on y is going to be equals to minus 1 to power n minus 2 factorial n minus 2 times x plus n. It should be divided by x plus 1 to power n. Now this question is slight bit difference. So understand this question properly. So see what is happening here. If we take that, if we see the question carefully, then there is a product basically. Y is supposed to be x time log 1 plus x. So by using the fundamentals on the Leibniz theorem, you can use the u and classify u and v like in this way. So you should take the u function supposed to be log 1 plus x, and you must take the v equals to x, because x is the only term whose differentiation is decreasing, and very soon it reaches to be into the 0 basically. So here is the classification on u and v. Now what happened? We need to apply the Leibniz theorem. You know, the n time differentiation on log x plus 1 can also be written as, see, 1 dn minus 1 upon dx minus 1 is there. I have taken out d by dx inside, and now we take the differentiation of log 1 plus x with respect to x. It should be 1 over x plus 1, correct? So it can also be written as x plus 1 to power minus 1. Now see what is happening here. You should take the x plus 1 to power minus 1 on n minus 1 time. So directly we can open up the n differentiation. How it possible? We'll explain later on, but from there, see, when I take one more time differentiation of this 1 plus x to power minus 1, basically I'm briefing you how this term basically possible. So if we take the one more time differentiation on 1 plus x to power minus 1, it should be, student, minus 1 of 1 plus x to power minus 2. This is the logic behind this. If we take one more time differentiation, then we take minus 1, then minus 2, and 1 plus x to power minus 3. So basically what is going on? The minus product of the natural number is increasing, and the power is also increasing here. So when we reach to the n minus 1 time, so what is happening here? Minus 1, then minus 2, then minus 3. It's supposed to be till the minus n minus 1. So here you can see minus 1 raised to power n minus 1. If I release all the minus, then what is happening? It is the product of the n minus 1 natural number, which supposed to be factorial n minus 1. I hope this term is now clear how it's possible. And suppose, student, this is what is happening here. This is 1 plus x to power minus 1. It should be written as 1 plus x to power 1 minus 2 can also be written as square. Cube can also be written as 1 plus x to power 3. So it should be till n. Okay. So this is basically n time differentiation on log 1 plus x is over, and we reach to this formula. Now, when we differentiate our v is what? V was x. We take 1. We get 1. When we differentiate v one more time, then we get 0. So there is no need to take the v till 2 time differentiation. So now open up the Leibniz theorem. Now how we use the Leibniz theorem here? So this is the n time differentiation on the product of x, then log 1 plus x. It should be n time differentiation on log 1 plus x. You must keep x as unchanged. Later on, in the second term, you should differentiate log 1 plus x 1 and minus 1 time. Then you must differentiate your x 1 time. So here are your answers. See, if you differentiate your u n time, then we get this answer. You must keep x unchanged. And then in the next term, if this is the n time differentiation of u, then this should be the n minus 1 time differentiation of u by changing whole n by n minus 2. And the differentiation of x here is 1. So basically, this is the end of this question. This is very interesting question. Basically, you can say another form of Leibniz theorem we have used here. Moving forward, I have another example. This example is very important in 2 marks in all AKTU Mathematics 1 university paper. So what is the question basically here? The example is, if y equals to x to power n log x, then we must prove that the n plus 1 time differentiation of this function supposed to be what? This is factorial n upon x. So let us discuss how this question can be solved basically. So first of all, student, when we apply the Leibniz theorem, obviously we need to differentiate this y higher and higher times. So let us discuss what is happening when I differentiate this y 1 time with respect to x. So as you can see, x is present in 2 different terms, or you can say 2 different functions. So let us design the first supposed to be 1 and the next function log x supposed to be 2. So how we get the differentiation of the product? It should be keeping the first same and differentiating log x with respect to x. We get 1 upon x plus, now we must take log x as unchanged and x to power n raised to n x to power n minus 1. No problem. So we can take this x common from the entire denominator and we must shift this x from right to the left hand side. It look like x y1, okay? X over from here and 1 more x added here. So the x power is n minus 1. By making 1 power, you can say add and minus, it should be what? X to power n, and then it should be ny, because y is given to us x to power n log x. So here if we get x to power n log x and the product of n is also there, then this is n. So it should be n of y. There you are. So now x y1 supposed to be x to power n plus ny. Now student, as you can see, there is a product of 2 variables. 2 variables mean x and y1, both the variable having x. So now we can apply the Leibniz theorem, right? So one more concept is there. How to apply the Leibniz on these 2 terms? So because as you can see, x is what? X is a variable and the first time differentiation of this x supposed to be what? 1 and second time is 0. And y1, what about y1? Y1, in case of y1, you can get any number of differentiation on y1. So we are going to suppose x as v and y1 as a function of u. Now, if I open up the Leibniz theorem, so this is the basically the main representation of Leibniz theorem. You must first open up the Leibniz theorem n times on both sides. Then you must mention the d to power n, right? Now we apply the Leibniz theorem on all the 3 terms. Here, what is happening? You must take the y1, the n time differentiation on y1. You must keep the x unchanged. In second term, this is the value of MC1. It is common in every Leibniz question. Now you must take the n minus 1 time differentiation of y1 and you must differentiate your x 1 time with respect to x. Then see, one more thing is there, student. When you take 1 time differentiation of x, it is 1. It can also be written as factorial 1, no problem. When you differentiate your x square 2 times with respect to x, it should be 2 into 1. Okay. And student, as you all know that 2 into 1 supposed to be, or you can say, can also be written as factorial 2. So what is happening here? When you differentiate a question like x to power 1 one time, then it gives you factorial 1. When you differentiate x squared 2 times with respect to x, it gives you factorial 2. So what is the logic here? When you differentiate a function n time having x to power n, it should be the factorial n. So this is the concept where the factorial of n is mentioned here. This is factorial n basically. Then the third term was here. You should keep n unchanged and you must differentiate your y n times. It should be yn. So all the three terms now resolved by the Leibniz theorem. So we must moving forward. It should be 1 on n should be yn plus 1. y1 on n minus 1 should be yn. This is factorial n. You can keep it same. Then this is n yn. What is happening? You can cut over the n of yn. So you get your answer. Yes. So it is another question on Leibniz theorem. Much amount of the Leibniz theorem, I hope you understand now. So if I have another example, so yes, I have another example. Student, this question is a very topmost priority based question for the university exam in higher marks. See, this is a question which is basically obviously repeated question in various university examination in 7 marks. This is the highest question marks. Okay. So let us read the question first. What is your question? Here, the y is given to you. Then you must prove that the yn plus 2 time of x square minus 1, then 2x time yn plus 1 or minus n of n plus 1 yn supposed to be 0. So student, let us discuss one very important thing here, right? And what is that? See, you can confuse, basically the Leibniz theorem in short form can also be written as LBZ theorem, right? So every question which is going to handle by the Leibniz theorem, always, what I said, always mention in these 3 notations, always, and you can say mostly. So whenever the question or whatever be the question which is going to solve by the Leibniz theorem, its answer must contain sometime yn, then yn plus 1, then yn plus 2. Along with this logic, there is another logic. And what is that? See, you can say this is your y at the same, or you can say at its current situation. This is not look like the very functional question for the Leibniz theorem, because in a Leibniz theorem you must get the product of 2 functions. As I can see, there is no product of 2 terms. So in its present situation or present form, this question is not applicable on Leibniz theorem. So what you should do for the Leibniz theorem, you must convert this question to apply the Leibniz theorem. And how you convert this question to be usable, or you can say to be convertible to the Leibniz theorem, the first logic is, whatsoever be the question on Leibniz theorem, you must differentiate at least one time with respect to x, so that you can get your question converted in the standard form of LBZ theorem. This is the very important logic behind the LBZ theorem. So let us differentiate this question with respect to x both sides. So it should be n of x square minus 1 raised to power n minus 2, and the differentiation of x square is supposed to be 2x, correct? Student, can we mention this question in another form? And what is the form? Let's see. I can mention it like 2nx, then I can keep the x square to x square minus 1 raised to power n here, and the minus power can also be written here, right? No problem. See what is going to happen. We can transfer this denominator from the right to the left side. It look like this, x square minus 1 with y1, okay? Then what is happening here basically? You see, this is 2n of x, and the rest term, which is x square minus 1 raised to power n, this is given to you as y. So I can transfer this term into y, and this look like this. Students, see very carefully what is basically happening here. Now, currently, from this equation where that question was given to you, you can see from the and from there. You can see this is the perfect form of Leibniz theorem. Now you can apply the Leibniz theorem very easily. Why? Because you have converted your question, your problem into such two terms where one term differentiation is going to decrease and the one time and the any number of mean from 1 to n time differentiation of the second term is well known to you in advance. So now this is the perfect form where we apply the Leibniz theorem. So let us apply the Leibniz theorem. Okay. So see, one more logic is here basically. I want to basically inform you. See, what is happening? Why we need to differentiate this question one more time with respect to x? Something is different here and something is going to happen, which we must understand in advance basically. See, if you open the Leibniz theorem n times on y1, it reach you till yn plus 1 maximum. Okay. So then how it possible that you will bring this answer on yn plus 2? If you open up the Leibniz theorem here n times, then the maximum term supposed to be happen and supposed to be present in your question is yn plus 1. So what is happening? And now to get the yn plus 1 to present there, you can do one thing, or even you can do basically more than one things. But the most thing is that you must differentiate your question, as we all know that by taking the differentiation on y1 is supposed to be y2. I have another method for you here. Student, sometime if require, you can apply your theorem more than n times. Remember this. This is very important concept. If require, something is happening, you can apply the n plus 1th time differentiation, mean the Leibniz theorem on any function. In that case, student, where you have used the nc0 in place of n, you must use the n plus 1. That is the logic. Then you must differentiate your function n time in u and you must keep v as same. The second term supposed to be nc1. In place of nc1, you must use what? N plus 1 c1. Then you must take n. And here also, student, one more thing is missing here. You must differentiate first time your u n plus 1 time. Then you must subtract 1 from this term. So you get n time differentiation of u. And now you must differentiate 1 time your function with respect to v. So if you are lagging behind with one term, then you can do two things. First is either differentiate your function with respect to x or open up the Leibniz theorem higher than 1 time, mean n plus 1 time. So now two options are there. So just simply going through with the first one, where we have differentiate this function with respect to x one more time. So partially differentiate, basically there are two terms, so you must differentiate. The x square minus 1 is same, differentiation of y1 is y2. Then the differentiation of x square is 2x and y1 keep unchanged here. 2n is a constant. First differentiation of y1 supposed to be y1, and then the differentiation of x with respect to x is here 1. The differentiation of x is 1. Okay. Now on these terms, you can apply now the Leibniz theorem. So student, see, two terms are there, similarly 2 and 2 terms are there. So you can very easily apply the Leibniz theorem here. See what is happening. So student, by converting or by assuming that this y2 is u function and this x square minus 1 is a v function, you must open the Leibniz theorem. So what is the statement? You must keep x square minus 1 as unchanged. You must differentiate your yn, y2 with respect to n times. So it's supposed to be yn plus 2. I hope you understand that. Then you can keep your nc1, which is supposed to be what? 1. Then you must differentiate y2 n minus 1 time. Then it should be yn plus 1. And the first time differentiation of x square is supposed to be 2x. So the second term is there. Moving forward, 2 is common here because we are going to differentiate your 2x with respect to x one time. So now this is what? This is your NC2, which is nn minus 1 over factorial 2. Then y2, you are going to differentiate n minus 2 time. The total supposed to be yn. Now the differentiation of 2x is only 2 here. This is the differentiation of 2x. So now if you differentiate 2 one more time with respect to x, you get 0. So the Leibniz theorem on this term is over here. Moving forward, then apply the Leibniz theorem on 2x of y1. 2 is the same. Keep x unchanged, and the differentiation of y1 n time is yn plus 1. Then keep differentiate y1 n minus 1 time, which gives you yn, and the differentiation of x is 1. Second term is also over. Moving forward to the right side, 2n is a constant. Differentiate y1 with respect to x n time. It should be yn plus 1. Keep x unchanged. There you are. Next, keep your yn and differentiate y1 differentiate n minus 1 time, which is yn, and the differentiation of x is 1. Correct? And this is 2n square of yn. First term, last term is this. 2n is a constant, and by taking n time differentiation of y, it should be yn. So I hope at the end we must basically combine all the common terms together, so we get a answer which is given in this form. So this is the only remaining part from this question now. So by taking all the terms, you can see 2 to 2 is over from here, and mostly terms are common. So take yn plus 1, the larger differentiation, then yn plus 1, then yn as a common terms. So you see 2n is 2n, cancel because plus and minus. Here I hope, yes, we can subtract this n square from 2n square. So the final answer is look like this. Hence this is the required answer basically which we have to prove. So student, this is the Leibniz theorem, where you understand how to apply the Leibniz theorem and basic little amounts of the shortcut on Leibniz theorem. So I believe that by taking these advice and this concept in your mind, you can go through with the examples and you can solve the remaining problem. Those are very important on Leibniz theorem. At the end, student, I must take this question because this is the last year questions and a very important question on Leibniz theorem. I'm going to only discuss the applicable form of this Leibniz theorem. When we get the applicable form, from there we can apply the Leibniz theorem. So here in this question, I will discuss the differentiation form of this question, because there is a problem, student. As in compare with the previous question, here you can think that there is 2 terms only. There is no doubt basically, but the things are slightly different. And what this is, in your opinion, maybe you, and in your opinion, maybe we. But if you are thinking like that, then unfortunately you are wrong basically. So what is the problem? Because student, the differentiation on both of the term, either it is 1 minus x raised to power minus alpha, or is it e to power minus alpha x, the differentiation is not going to end at any number of place. You are simply going to differentiate, but the terms are not supposed to be ended over there. So there is another logic in this question. So first, student, let us assume that the given question is y. Okay. Now differentiate, as I only advise you, then wherever you find uncompatibility in your question, you must first differentiate your question with respect to x. Things slightly comes to your way, but first you should differentiate your question. So as I have mentioned, I am going to differentiate this question, but the problem is both the terms containing x. So we must use the product rule basically. Okay. So student, this first is same here. Okay, maybe e raised to power alpha x treating first, or maybe the first term is treated as second. So e to raised to power alpha x is same here, and the differentiation of 1 minus x to power minus alpha is what? 1 minus what? 1 minus x to power minus alpha, and then 1 more alpha. See, here you are. Then this time we must differentiate e raised to power alpha x, which is e to power minus alpha x into minus. There you are. In place of plus, you should have minus here. Student, do one thing. Please take this entire term as common from these two terms. You can take the common terms. Why I have taken out these two terms as a common? Later on, we can replace the product by y equals to. So if we get x 1 minus x to power minus alpha as common, right? And e to power minus alpha x, what happened? Here you can have alpha only, right? With this is minus power alpha of, and there you can see minus 1 power is also there. So this can be written as 1 upon 1 minus x, correct? Here we have, as we have taken this entire term as common, so you get only what? Alpha. If you take alpha also common, then you get minus of 1 here. Okay, so now take product of 1 minus x here, so it should be x upon 1 minus x. Kindly transfer this 1 minus x from denominator to the numerator on left hand side. It can also be written as y1 time 1 minus x. And now what is happened? This is your alpha, this is your x, and it can also be written as alpha xy. This is the perfect form of Leibniz theorem. So by taking this third example, student, now I am confirmed that you get the main concept behind the Leibniz theorem, then how to assume the important term, how to and where to differentiate, what is the logic behind differentiation of each and every terms. So these are little amount in shortcuts on Leibniz theorem. Here I have used the 2-3 beyond the limits, you can say concept. By using that concept, you can get your all type of Leibniz theorem problem resolved. I hope so. So student, at the end, we must apply the Leibniz theorem on this question now. As you can see, both side, the left hand side and the right hand side, having double terms, mean the product of two terms. So these terms are very, very applicable on Leibniz. You can open up the Leibniz theorem. Lastly, I'm going to tell you one more agenda which I have already basically informed you. See, this is y1. And here you can get y only. So if you open n time Leibniz, what is happen? If you open the Leibniz theorem n time on y1, then it gives you yn plus 1. If you open up the n time Leibniz on y, then this term gives you yn. So at this stage, if this is equation number 2, at this situation, this stage, if you apply Leibniz on n times, then according to Leibniz at this situation, the yn plus 1 be the largest derivative of y. You can see your answer which you should prove, which is also containing the largest derivative as yn plus 1. So this is the last agenda, and you can say the last shortcut on Leibniz. First, before applying the Leibniz theorem, you must recall, you must go through that how many times you're supposed to use the Leibniz theorem. Okay, so here basically you must differentiate n times on both sides by the Leibniz theorem. Okay, this y1 can denoted by as u function, and this 1 minus x supposed to be denoted as a v function, because this differentiation is going to decrease, right? So student, y1 on applying n time Leibniz converted into yn plus 1. In first time, you must keep x1 minus x as same. Now this is nc1, and you must apply n minus 1 time differentiation on y1, which gives you yn, and the 1 time differentiation of x is minus. So this is the reason you get minus here. The left hand side is resolved by Leibniz theorem. Moving to the right side, alpha is a constant, yes. Then on xy, you must keep x unchanged, and you must apply n time Leibniz on y, which is yn. Then plus nc1 gives you n. Then alpha obviously same. Now the differentiation of y1 n minus 1 times gives you yn minus 1, and 1 time differentiation of x gives you what? 1. So this is over from the left right hand side also. Now you can manage, or you can merge all the common or sub non-common terms together. Maybe yn plus 1 is the last highest term, and which is alone always. Then yn may be present on more than 1 or 2 times. So there you can see yn is present on 2 times. So you can take yn as common, and alpha n y to power yn minus 1 is the last term and only term here. So it can be mentioned as, hence you get your answer. So student, this is all about the Leibniz theorem. I hope you get this lecture very easily, and you get some knowledge by going through with this lecture. So thank you very much. Jai Hind.